Welcome back to Physics 141 Online. There's one more topic that we need to discuss in our treatment of rotational dynamics. And we have already come up with rotational versions of kinetic energy, rotational versions of force, which is torque, and now we want to look at a rotational analog to momentum. And we're going to come up with a quantity called angular momentum, which is really useful in analyzing the behavior of rotating systems. The starting point is to go back to our definition of torque and to express torque in the form of a vector. So once again, we're looking at an object here of arbitrary shape that can rotate around an axis going through the origin. And we're going to look at one piece of the object shown here as a square. If we use our definition of torque as force times the perpendicular distance away from the axis, we have this familiar equation, and that's in the form of a scalar. But we can also express this in terms of something called the cross product of two vectors. If we understand the vectors to be the force vector F and the radius vector or position vector R. F, of course, is along the line of the force that's applied to the object at this point. R is the position vector that tells us where the point is where the force is applied to with respect to the rotation axis. So the definition of the cross product, see, this is a little bit different from the idea of a dot product, but similar in some ways. The cross product has a magnitude, and the cross product of two vectors A and B, and we read this as A cross B, the magnitude of it is magnitude of A times the magnitude of B times the sine of the angle between the two vectors when they are drawn tail to tail, as shown here. So in order to get the right angle to plug into this equation, you have to draw the vectors tail to tail, which is why you can see in the sketch why theta is labeled the way it is. If I take the r vector and slide it along the radial direction, I can draw those two vectors tail to tail, and theta is the angle between them. The direction of this vector is given by something called the right-hand rule. And if you haven't encountered this before, if you've never seen a cross product, you have to get used to this. The way it works is you extend the fingers of your right hand along the direction of the first vector. And up here the first vector is r, the position vector. So fingers of the right hand along r, and then you curl them toward the direction of the second vector, which is f. So if you take your fingers of the right hand, point them along R, curl them toward F, that's in the counterclockwise direction. The direction of your thumb is the direction of the cross product, and in this case that should be out of the page. Remember, it's your right hand. So we're going to use this method for designating the direction of not only the torque vector, but also the angular velocity and angular acceleration vectors. And the way it works is your fingers curl around in the sense of the rotation, and the thumb points in the perpendicular direction, and that actually then is the direction of the torque vector or the angular velocity vector or the angular acceleration vector. Now, we're going to go back to Newton's second law and show how we can express something very similar using torque. Remembering Newton's second law says that if we add up all the forces acting on an object, and we'll just indicate that net force as F here. Remember that it looks like it's just a single force, but it really represents the sum of all the forces. That's mass times acceleration. Acceleration is the time derivative of the velocity vector. And the m here, as long as the mass of the system is not changing, we can put the m inside the quantity that we're differentiating, and it doesn't change the meaning of it at all. And we remember that mv is the linear momentum p. So we see that there is a nice, very natural way of writing down Newton's second law as the net force being equal to the time derivative of the momentum. Well, we can write the net torque of an object like this. Torque is r cross f, where f represents the net force. So that would be r cross dp dt, because as we see above, F can be written as the derivative of P with respect to T. So that's the net torque. Now, there's a distributive law for cross products, and it works like this. If we take the time derivative of the quantity R cross P, then there's kind of a product rule that works here where we end up with the derivative of the first quantity crossed into the second quantity, plus the first quantity crossed into the derivative of the second quantity. And the order is important in cross products. And so we have to take that into account when we write these expressions down. Now, why are we doing this? Well, we notice that the second term on the right-hand side of the equation is exactly our torque vector. Okay? So now what we're going to do is solve for that second term on the right-hand side, and it's equal to, as we see on the next line, it's equal to the term that's on the left-hand side minus the first term on the right-hand side. Okay, so we just did a little algebra here to solve for this quantity r cross dp dt, which is the torque. And one nice thing about this second quantity on the right-hand side, dr dt is nothing more than the velocity vector, v. And v cross p turns out to be 0. The reason is that v and p are in the same direction. Remember that p is mv. So whenever you have a vector crossed into itself, you get 0 because the sine of the angle between them is 0. And the sine of 0 is 0. So that makes it really easy then to write down this torque as simply the first term on the right-hand side. So the net torque on a system is the time derivative of r cross p. So that's what we start with on the next slide. And because of this, it turns out to be useful for us to define this term on the right-hand side that's inside the parentheses. And we call this thing the angular momentum because it's very similar, it behaves in a very similar way for rotational motion that momentum does for a system that's in linear motion. L is the symbol for angular momentum, so we make the definition that L is equal to this cross product of the position vector and the momentum vector. And when we do that, then we can see that we can write down Newton's second law. The net torque on the object is the time derivative of this quantity that we've now called the angular momentum. And why it makes sense to call it the angular momentum is pretty clear when we compare the torque equation to Newton's second law. For translational motion, the net force on an object is the time derivative of the linear momentum. So now for rotational motion, the net torque on a rotating object is equal to the time derivative of this quantity, and this is why we call it the angular momentum, because it plays the same role in this equation as the linear momentum does for translational motion. So comparing those two gives us yet another analogous quantity for rotational motion. Let's just survey these again. In translational motion, S or x represents the position for an object. In rotational motion, we use the angle theta. V in translational motion is replaced with omega in rotational motion. Linear acceleration in translational motion is replaced by angular acceleration alpha in rotational motion. Mass is replaced by moment of inertia, which tells us something about how hard it is to get the object to be rotating. Kinetic energy of translation, well, there's a rotational counterpart to that as well. 1/2 mv squared is replaced with 1/2 I omega squared. Force in translational motion is replaced by torque in rotational motion, and now we've got two ways of writing down the torque. R perpendicular F is fine for the magnitude of the torque, but R cross F is the vector expression for torque. And now finally, linear momentum P is replaced by angular momentum L. And notice that tau and L are both equal to the position vector crossed into the vector that was the one for translational motion. So tau is R cross F, L is R cross P. So these are this kind of a table is of real great assistance in remembering the equations that come out of rotational dynamics. As we've stressed in class, if you're trying to remember a rotational formula, it's useful to go back to the translational formula and make the appropriate replacements so that you can come up with the rotational form. Now, just as Newton's second law for translational motion was important because it gave us the law of conservation of momentum, the second law for rotational motion gives us, under the right conditions, the law of conservation of angular momentum. And this is the third great conservation law of classical physics. We started with conservation of energy, and then we showed that under the right conditions, momentum is conserved, And now we're going to see that satisfying certain conditions, angular momentum is conserved for a system. So remember, from Newton's second law, the net force is equal to mass times acceleration. But here, casting it in terms of the time derivative of momentum, the net force is dp dt. And if the net force is zero, then momentum is a constant. No matter what happens to a system, if you have a collision of two particles, the total momentum of the system is going to be constant before and after the collision. Now, looking at Newton's second law for rotational motion, the net torque is equal to the time derivative of the angular momentum. And if the net torque is equal to zero, that means the angular momentum is constant. And hopefully it's pretty clear why this works, right? Because dl dt, which represents the torque, that's the time rate of change of L. And if that's zero, that just means L doesn't change. L is a constant. So in practical situations where we're using this law in order to analyze the behavior of a rotational system, saying that L is equal to a constant is equivalent to saying that L initial, before some kind of interaction, is equal to L final, which is the angular momentum after the interaction has taken place. Now, let me give an example. Here's an example where there's a hanging rod. It's a uniform thin rod hanging from a hinge in the vertical position, and there's a ball of mass m and initial velocity v0 that hits the end of the rod and sticks to it. And of course, it's pretty obvious what's going to happen after that ball sticks to the rod. The ball plus the rod's system is now going to rotate. And the question that we'd like to try to answer, because this is a situation that we could actually do an experiment on, we would like to know what would be the angular velocity of the system after the collision takes place. And it's always important to define what we mean by system. Here the system is the rod or the stick plus the ball. So let's ask ourselves, what conservation principles could we use to analyze this collision? So is mechanical energy conserved? And the answer, of course, is no, because this is an inelastic collision. The only way the ball could stick to the rod is if some kind of deformation happens, which means that energy would be lost. Mechanical energy would be lost. So mechanical energy is not conserved in this collision. Is linear momentum conserved? In other words, is the linear momentum that the ball has equal to the linear momentum of the system after the collision? And here the answer also is no. Because remember, for linear momentum to be conserved, the net force acting on the system has to be zero. Well, the system is the ball and the stick. And it turns out that when the stick begins to rotate just after the collision, there has to be a force that points toward the center of the circle. And that force is supplied by the hinge or the pivot. So the rod plus the ball is experiencing a net external force during that collision. So linear momentum is not conserved. What about angular momentum? The condition for angular momentum to be conserved, we just learned, is that the net torque on the system is zero. And here we can say yes, because the force that the hinge supplies, that is acting on the rod plus the ball, is along a direction that passes through the rotation axis, which means even though there's a force, it doesn't produce a torque. So we can look at this system and say, okay, write down the angular momentum of the system before the collision, write it down after the collision, and then set them equal. But the question that comes up is, how do we calculate the angular momentum for the rod? We know how to calculate the angular momentum for the ball before the collision, because if we define a particular rotation axis, that tells us the position vector r, and we can use the definition of angular momentum to find out what it is before the collision. But after the collision, the only thing we have is pure rotational motion, because the ball and the rod are stuck together. So how do we calculate L for the rod? Well, let's go back to our picture of this arbitrary rotating system and imagine that you've got this object made up of lots of little mass pieces, delta m, and the whole object is rotating with an angular velocity omega. So that means each piece has its own linear translational velocity v. Well, the tiny amount of angular momentum associated with this mass delta m is, of course, r perpendicular times the momentum for that piece, which r perpendicular is just the radial distance away from the axis. So that's r sub I in my picture. P sub I is nothing more than the mass times the velocity. So it's delta m sub I times v sub I. That gives me the angular momentum for that little piece. Well, let's substitute in v sub I equals r omega, and then what we'll do is sum up the angular momentum of each of the pieces to give us the total angular momentum of this entire object as it rotates. So total L is the sum of all the individual pieces of angular momentum, and now we take the expression from the top line, substitute in v sub I is r sub I omega, and we end up with r sub I squared delta m sub I times omega. The omega is the same for each piece because every point on the rotating object has the same angular velocity. So omega comes outside of the summation, and look at this. That summation is the same one that we've seen before when we were calculating the kinetic energy of rotation. And so that's just the moment of inertia I. So we see here for an object that's undergoing rotational motion where the axis is fixed in place, the angular momentum of that system is just the moment of inertia times the angular velocity. And this also looks like something analogous to linear motion. When we had linear motion, we wrote down that the linear momentum was mass times velocity for a particle. Here, for a collection of particles that rotate around a fixed axis, P is replaced by L, M is replaced by I, and V is replaced by omega. So, going back to the original slide where we wanted to find what the angular momentum would be for that rod after the collision, all we would have to know is what's the moment of inertia of that system and what's the angular velocity. So now we have a way of going back to finish that example problem. What we've done here is we've defined a vector definition for both torque and for angular momentum, and we've shown that there's a new conservation law. If you've got a rotating system and if there's no net external torque on it, then the angular momentum stays the same. And so what I will do when we meet in class is finish up the example problem using the law of conservation of angular momentum. I hope this is a good introduction for you into angular momentum, and we will use this in analyzing some collision problems for systems that are rotating. I'll see you in class.